everyone, we're back with video 6.1.3, the last in lesson 6.1. So let's get started at looking at our enthalpy of reaction, our change in our enthalpy of reaction. So example 3, we're going to consider this reaction, 2SO2 plus oxygen gas goes to 2SO3. These are all gaseous. And we're going to look at 4 different ways of calculating your change in enthalpy here, 4 different methods. So method A is the experimental approach to determining the enthalpy of the reaction. Remember, this is a molar enthalpy, so all these delta H's are always per mole. Now, a 9.71 gram sample of SO2 gas reacts with excess oxygen, and that releases 15 kilojoules of energy. Calculate delta H of reaction. Now, knowing that this is a molar quantity, I want you to try to pause the video and calculate this here. So remember, this is your heat per moles. So pause this, try to work out this problem, and then come back to check your work. All right, welcome back. So to calculate our enthalpy of the change in our enthalpy of our reaction, we're going to put the heat of the reaction in the numerator and the number of moles in the reaction as the denominator. So that is going to be our kilojoules per mole there. That's the units we're going to want to end up in. So just plugging everything that we're given in, we know we have a 15 kilojoules of energy. Now the sign is important there, and since this says it's releasing energy, this is exothermic, meaning that sign is going to be negative. So negative 15.0 kilojoules, and that's on top, that's our heat. Now the number of moles, so how many moles do we have? Well, we don't know the moles, it's not given to us, but we can easily convert that. So we'll have our grams here, 9.71 grams, and that's of our SO2. And we'll just do our conversion in line using our molar mass, 64.07 grams of sulfur dioxide. And remember, this is from the periodic table per 1 mole, and now we're in moles, so now we're in kilojoules per mole. Now, this is a molar quantity per reaction, so we're in moles of sulfur dioxide, but we want moles of reaction. So for this one, we do need to look at the balanced chemical equation here. So we have 2 SO2s here for this entire reaction. So for every 2 moles SO2, we have 1 mole of the whole reaction. And just canceling out our units, we have grams here, moles SO2 there. Plugging all of this into our calculator, we get negative 198 kilojoules per mole of our reaction. Let's write reaction there. Okay, so there's our answer for part A. So that's the way that we can figure this out experimentally. Now the next method we can do is the products minus reactants approach. And it's pretty much exactly what it sounds like. We're going to take the heats, or we're going to take all the enthalpies of the products, and we're going to subtract the reactants. So, using the delta H reaction from part A, determine the value of HF for SO2 gas. Delta HF for SO3 is given to us here, negative 398 kilojoules per mole. This delta HF, what this means, right here. What this means is this is the enthalpy change when 1 mole of a compound is formed from whatever its constituent elements are. So from sulfur and from elemental oxygen, for example, in this case. So let's go ahead and figure that out. So our delta H of reaction is equal to the change in enthalpy of formation of the products minus delta HF of the reactants. Okay, plugging this in, we have 2 of our delta HF for our SO3, and I got that 2 from the balanced equation up here. That's our coefficient. Minus, let's put all this in brackets here so we can keep this straight, minus 2 times delta HF of SO2, so that's our reactant, plus 1 times delta HF of O2. So this is probably a very good time to mention that the heat of formation or the change in enthalpy of formation for any pure element at standard state is always 0. And so a pure element would be only oxygen, like O2, or only fluorine, or just sodium metal, for example. So all those are just the plain pure element. So we'll write ourselves a little note here. Delta HF, pure elements at standard state is always 0. Okay, back to our calculation. We know our delta H of our reaction here. So we figured that out before, right up here, right? So we're using the delta H reaction from part A. So just plugging that in, we get negative 198 equals 2 times negative 396. So that was given to us here. Minus 2 times delta HF, SO2, what we're trying to find, plus 1 times the heat of formation of oxygen, which is a pure element, so it's 0, so plus 0, 1 times 0, done. Plugging all of this into our calculator and rearranging, we're going to find our change in enthalpy of formation for sulfur dioxide. And that should come out to negative 297 kilojoules per mole. Okay. So those are the first two methods, experimental and products minus reactants. The next one is Hess's law. You may have used Hess's law before, you may not have. Hess's law, this turns out to be very, very handy when you're trying to figure out the delta H of reaction for a certain reaction, and you have a bunch of related reactions, and you know those delta HFs. So what we're going to do is look at how we can manipulate these three equations and kind of form the one that we want from it. So we want to combine all of these reactions in some way by reversing them, by multiplying them by a certain amount, by dividing to get the original reaction. So for here, what we want to do is we want to combine these reactions to get the original reaction. Okay, and so the reaction we're trying to find is the one given at the very top. So right here, we're trying to find our delta HF for this entire reaction. Notice that's not one of these, but there are certain compounds that exist in these three reactions. So what do we do to these reactions to get them to match up? Well, if we look at reaction 1, so we know that this has oxygen in it. It looks like it has H2O in it. It has H2S, SO2. And I'm just going to focus in here on the SO2, that sulfur dioxide. In reaction 1 down here is in the products. But we want it to be in the reactants to match our original reaction. So what we can actually do is flip this entire reaction, just reverse it. So I'm going to reverse reaction 1. So reverse 1, and that 1 just stands for number 1 here. And then I'm going to write it out over here in reverse form. So 2, H2O. So again, we're starting with our reactants and making them starting with our products, making them reactants. Plus 2, SO2 yields 2, H2S plus 3, O2. Now, whatever we do to the reaction, we also have to do to the delta H. So for our delta H, since we reversed it, we're actually going to reverse the sign. So our new delta H, I'm going to take the negative, I'll write this in a different color so we can kind of keep track of what we've done. So negative delta H1, and that's going to equal, because it was negative over here, so a negative is a positive, so positive 1124 kilojoules per mole. All right, so that's our first reaction. Let's look at our second reaction. So in this reaction, I notice I have SO3, right? So my SO3 over here is in the reactants, but look, I want it in the products. So I'm going to need to flip that around. I'm also noticing but I have 2 of them. I really need 2 of them. And here there's only 1. So I'm going to reverse it, and I'm also going to double it. So I'm going to multiply the entire reaction, including the heat of the delta H, by 2. So this one I'm going to reverse, and I'm going to double reaction 2. So just reversing it and writing it out, I have H2SO4, sulfuric acid. But remember, I'm doubling it, so 2 H2SO4 now. And that's going to yield 2 water. And, let's see, 2 SO3. And then, of course, I reversed this. And I doubled it, so minus 2 times delta H2. And if we do the math on this, 132 times 2 is 264. Change the sign, it's positive. So we get positive 264 kilojoules per mole. Okay, reaction 3. For our reaction 3, I notice that everything is actually on the side that I want it to be on. I have my oxygens here on the left, and I need my oxygens on the left on the reactant side. But I notice I need to double it because here the coefficient's 1, here the coefficient's 2. So I'm going to double it. So I'm going to double reaction 3. And just write it out in the same way, the products minus reactants. We're not flipping it this time. So 2 H2S, that 2 because we're doubling it, plus 4 O2, it's going to yield 2 H2SO4. And then the only thing we need to do was we need to double it. So I just added a positive sign there. I'm keeping track of my signs, but that won't change the sign over here. So let's see, 793 doubled equals, what is that, negative 1586 kilojoules per mole. Okay, so now that we have all of our reactions written out, we're going to start crossing things out and making sure we have everything we need here. So overall, I'll do my overall reaction. And remember, we want the overall reaction to end up being the one at the very beginning, the one I highlighted right up here. We're going to want these to match. So let's see if we can get that to happen. So I have my 2 H2S on the product or the reactant side. I'm going to cross my 2 H2S out on the product side. Got rid of those. Okay, what else cancels out? Oh, 2 waters on the reactants, 2 waters on the products. Those are gone. 2 sulfuric acids, 2 sulfuric acids. Gone. So I have 3 oxygens, and I have 1 oxygen left over right here because 3 or 4 minus 3 is 1. So I'm left with my 2 SO2, my 1 O2, my 2 SO3, which is what I needed. So on my reactant side, I have 2 SO2 plus O2 gives us 2 SO3. Now, why did we go through the trouble of doing all this? Well, that's to figure out what the delta H of reaction is. So we wanted the delta H of reaction of our original reaction. And the reason that we shuffled all these around was so we could manipulate these numbers to get the number we want. So now the only thing we have to do is add all these up. And when we do, we get negative 198 kilojoules per mole. And that's for our mole of our reaction. And if we look at that number, it's exactly the number that we had for our experimental reaction. So we know we're on the right track. Okay, our last approach that we're going to take is the bond energy approach. And this one I think is the most interesting because we're going to be actually looking at the energies of making and breaking bonds. And I want you to notice we are given our bond energies here. Here's our bond energies for our 2 different kinds of bonds we're going to be dealing with in this reaction. And we're going to refer to those a lot. So I'm just going to rewrite our equation, the same equation we had at the beginning of here. So we don't have to keep going up. Actually, it's right here. We can just look at it right here. All right, so use the following structures and the bond energies, calculate the delta H of reaction. Compare the result with that found in part A and explain any difference. Okay, so what do we need to do for this reaction to take place? I like to do this on a separate sheet of paper so I can show you a bunch of, so I can really expand out everything we're going to be looking at. So I'm just going to rewrite the reaction here. So 2 SO2 plus O2 yields 2 SO3. Now we're given the Lewis structures for these, so I'm just going to write these as Lewis structures. We have 2 SO2 molecules, so I'm going to write both of them. So 2. Okay, so that's one of them. Here's the second one. All right, and then plus O2. Well, here's our O2 Lewis structure. This one's not given to you, but this one's pretty simple to figure out. And this is going to yield 2 SO3s, and SO3 is given to us there. So SO3. And we have 2 of them. Okay, so now we have to figure out how many bonds we're breaking and how many bonds we are forming. So I'm going to start with breaking bonds. So to break everything apart on the reactant side in order to get to products, because we have to break all these bonds in order to make the bonds. How many bonds of SO2, how many SO2s are we going to break? Well, let's see. 1, 2, 3, 4. So 4 SO bonds are going to get broken there. Bonds broken. And 1 oxygen bond broken. 1 O2 bond broken. And then let's look at our product side. How many bonds are going to need to be formed? Because now we have a bunch of oxygens and sulfurs floating around. They need to connect together. So we have 1, 2, 3, 4, 5, 6. So we have 6 SO bonds formed. Okay, so keeping that in mind, that is how we figure out the bonds that we have broken and that we have made. So I'm just going to write the bonds we've broken and the bonds that we've formed right here on our notes page. So we need to break 4 SO bonds. And when we break those 4 SO bonds, we can do a calculation and see how much energy that was required to break those bonds. So positive, because energy going in, endothermic is positive, plus 4 for 4 bonds times the bond energy of the SO bond. So here's the SO bond. There's bond energy, 522 kilojoules per mole. So 4 times 522 gives us 2,088. That's a positive number. Okay, next up, let's look at our oxygen. We broke 1 oxygen bond. 1 O2 bond is broken. So we break 1 oxygen bond. And again, that's positive because endothermic for breaking bonds. We have to put energy in to do that. And the oxygen-oxygen bond is 495 kilojoules per mole. Okay, and then just times itself, we get a positive 495. All right, and then we form 6 SO bonds. So we form 6 SO bonds. Now, when we're forming those bonds there, that's exothermic. It's releasing energy. Then we form 6 of them, so minus 6 times that bond energy again, which is 522. Doing the math there, you should get negative 3132 kilojoules per mole. And now the only thing you have to do to figure out the delta H of reaction is add all these up. So the delta H of reaction here equals negative 549 kilojoules per mole. So that was our calculated answer. Now the second part of this says compare the result with that found in part A and explain any difference. So I would like you to go right now and look at part A right up here and figure out why this is different. So think about, why is the answer different? Why is it not negative 198? So think about that, jot down some of your thoughts, and then come back to the video. Okay, so if you thought about intermolecular forces or interparticle forces breaking and forming, then you would be correct. So this is different because it does not take into account interparticle attractions that are breaking or forming. So none of those ion dipole attractions that we talked about. It's not taking into account any hydrogen bonding, van der Waals interactions, none of that. None of that is taken into account, just the bonds that are the covalent bonds in the actual compounds. And we know there are other forces at play. So it does not take into account interparticle forces or attractions that are breaking or forming. So there's going to be a difference there versus the real world. All right. Last part of the bond energy approach. We're going to do a bond energy graph. So draw the graph of potential energy versus internuclear distance. So how close the nuclei are to each other for both the SO and OO bonds, and to show why the energy for SO is greater than that of OO. Okay, so the potential energy is going to be on the y-axis here, and then on the x-axis we're going to have internuclear distance. Okay, I'm going to color code this so it doesn't get super confusing. So the first one we're going to look at is our OO, our oxygen. So I'm going to draw this and then we'll explain the reason that it looks the way it does. So we have this potential energy well going down pretty low, and this coming back up and leveling off when it gets pretty far away. And then that's going to be for our oxygen. OO. So that's that bond. And this is, of course, the distance that they are away from each other, and then this is the potential energy. Now we're going to look at sulfur to oxygen. So that potential energy well is lower, and it's shifted over. And then it levels out when they get far away from each other's potential energy, and when they're too far away, it's pretty much near zero. Okay, so why does this happen? And this is our SO bond. And then these at the bottom, these areas at the bottom, these are called potential energy wells. If you can think of a well, like a well that has water in it, like deep at the very bottom. So these are PE for potential energy wells. And that's where the potential energy is the lowest. And that is, of course, where we're going to have a bond. Now, the potential energy well right here, which is the base of the curve, that represents the ideal separation between the two nuclei. And so that ideal separation between the two nuclei maximizes the attractive forces and minimizes the repulsion between the atoms. Therefore, that is the most stable point, and that is the distance that the bond is going to be formed at. Because when the potential energy is lowest, a bond is going to form. That's when it's the most stable. So we'll write that down first. The potential energy well which is the base of the curve that we labeled, represents the ideal separation between two nuclei that maximizes attractions and minimizes repulsions between atoms. Okay, so then why does oxygen have a shorter bond length than sulfur-oxygen? Well, that's because it has a shorter internuclear distance because they're smaller atoms. So the oxygens are smaller than the sulfurs, so they can get closer together. So oxygen also has a higher well, so it ends a little higher up. We notice the potential energy is a little bit higher because it has a smaller bond energy, and you can see the bond energies right here. It has a bond energy that is smaller. So that means the bond energy is closer to zero, because this is our zero right here. This is inversed. So our bond energy for oxygen is lower. That's why this curve is higher up, but it's got a lower energy. It's closer to zero in the middle. So oxygen has a shorter bond, which means it has a shorter internuclear distance. Because they're smaller atoms. Oxygen, oxygen, or dioxide also has a higher well because it has a smaller bond energy. All right. So that is the conclusion of the 6.1.3 notes, and that is the conclusion of all of the 6.1 lesson. And thank you for your attention. Have a great day.